John from Capital One, and his interesting fact is he was once
Wait. He was doing like
No.
You're getting it wrong.
No,
I'm not getting it wrong.
It's not good.
Okay.
I know what I'm
Well, you
doing.
pronounced it John with an H. It's John, just Jon.
Right. The bad jokes are going to happen all day long.
I hope so. Yeah. Wait to get to the talk.
And his interesting fact is he was once run over by a Star Trek captain.
Yes.
There you go.
And John.
That's later. Question period. I got to have something for that. All right, let's see. All right, so good. Hi, everyone. My name is Jon Bodner. I'm a software engineer in the Tech Fellows program at Capital One. Thanks for coming out today. Before I begin, I want to start with a few quick questions. So show of hands, who came to Go from Python, JavaScript, Ruby, one of the dynamic languages? Good, all right. Who came to Go, another question, from Java, C#, one of the statically typed languages? Good mix of both. One final question. Who's ready for one more conversation about generics in Go? That many. That's good for me, at least. Great. Topic just doesn't go away, does it? So my goal today is to take a different approach to the generics debate. I don't particularly care about what syntax is used to represent generics. Instead, I'm going to talk about situations where generics make it easier to solve problems, a way to address some of those shortcomings, and what trade-offs have been made in other languages in the name of generics. And for those of you who came from the dynamically typed languages, this whole debate probably seems like a bunch of squawking, right? You got along just fine without type declarations at all. And then you get to Go, you don't really find any value in them, right? There's seems like plenty having a couple of type declarations you already have. So I'm from the Java world myself, and to those of us who came from Java or the other statically typed languages, generics are just much more important. We're already used to type declarations. We were already used to marking up every field in every class, declaring exactly the types were for every method. And to be honest, it's nice to just look at a method definition and know exactly what the code is going to do. And to be honest, it's also nice to have IDEs that can autocomplete for you and put little red squigglies under things that are wrong. And once you're used to types and putting types everywhere, it's really only a small step to wanting generics and reusing that same code across different types and having all of it checked for you by the compiler. And if you want to be pedantic, you could say Go already has generics. I mean, slices, maps, channels, arrays, they're declared with types, and the built-in make and new and copy and append and delete functions, they're all able to work with these built-in generic types. But that's intentionally missing the point. When people say they want generics in Go, what they want is the ability to add generics that work across all types, user-defined or built-in. And the good news for those of us who miss generics is that it does look like user-defined generics are on their way. At GopherCon this year, as Steve mentioned, Russ Cox announced that the Go team is in the process of looking at new backwards-breaking features for Go that will become part of Go 2.0. It's not going to be a wholesale change to the language. Maybe 2 or 3 new things are going to show up, so don't worry. Go is not going to turn to Haskell or Scala. Nobody wants that, right? Okay, good. But there's a good chance that one of these new features that will be added will be some version of user-defined generics. However, Go 2.0, it's still a dream, right? All of the discussion about adding generics to Go doesn't help anyone today. You know, I'm writing code now. I want to have a solution that makes my code less repetitive and more type safe. So what do you do today to solve this Go generics problem? And there are, broadly speaking, 2 things that people want to use generics for. The most common request is for generic data structures. I mean, slices and maps, they're handy, but sometimes you need something else, like a tree or a linked list or, I don't know, a performant concurrency-safe map fit for inclusion in a standard library. Little things. And if you want a generic data structure in Go, you have a few choices, and there's just all trade-offs for all of them. The first option, just write the same data structure over and over for each type that you need. This works out OK for simpler data structures. You can just copy and paste them. But no one really wants to copy and paste a skip list or a treep. And to support these more complicated data structures, you can use an ahead-of-time code generator. And there are lots of people in the Go community who like using code generation, but personally, I'm not a fan. Generated code is this weird in-between state. You run part of your build process sometimes, so you can check in the output of it. And if you have to make a change, so something requires you to regenerate the code again, you got to rerun the regenerator. And then you have to remember to check it in. I always forget. I like a simple build process. It's one of the things that I like about Go. And so the most common way to handle generic data structures in Go is just define your type once using empty interface, and you cast values in the return from the structure. And to be honest, this isn't such a terrible option. Casts are ugly, sure, and there's a performance cost, and in theory, they could fail at runtime. But in practice, this usually isn't the case. We don't usually put heterogeneous data into data structures, so casts don't usually fail. And while there is overhead in casts, chances are the performance cost of a cast is not the major bottleneck in your program. So generic data structures, they're nice to have, but they're not really essential. And that brings us to the other use of generics, which is technically called parametric polymorphism, but I'm going to call generic functions. And if there are any old school lispers in the audience, I apologize for stealing your term. What I mean by generic functions is a function where the algorithm is independent of the type of data being processed by the algorithm. And to me, this is a much better reason to add generics to a language. I mean, rather than just storing different kinds of values, sometimes you need to run the same algorithm over different data types. And when the algorithm is simple, maybe this is no big deal. You just make copies of the code. I mean, after all, one of the things that Rob Pike included in the Go proverbs is a little dependency is better than a little copy is better than a little dependency. Almost got that backwards. But this isn't dependency, it's just repetition. And as software developers, there's something we just find grating about repetition, right? There should really be some way around it. And at first glance, it looks like we're stuck. Without generics, we're doomed to keep on repeating ourselves, even when the logic is identical. But there is, to me, an approach which I think feels like the Go way. So if you've never run into this issue before, you maybe think it's just one of those pointless exercises gets people all riled up on Twitter. But there are real-world cases where this happens, and this is what happened to me. So one of the projects I work on is called LGTM. It's a fork of LGTM, the open source project that helps teams enforce their code review policies via GitHub. And as part of its integration with GitHub, LGTM allows you to specify a GitHub team as a list of possible approvers for a pull request. And to implement this, LGTM calls several different GitHub APIs to return lists of different things, like lists of users or lists of teams. And so, for example, here's our getTeamMembers function. In this function, we take in a GitHub client, a GitHub repo, and the name of a GitHub team. And we return back the set of the names of the members of the team. First, we call the client to the list of all of the teams for the repo's owner. We loop over all of the teams to find the one whose name matches the one that was passed in, and we store off that ID. Then we take that ID, we call the GitHub client a second time, get all the team members for that team with that specified ID. And then we build out a set of all the names of the users on that team and return back the set. Pretty simple code, really, once you break it down. And we thought this code was working well until we got a bug report in. So a new user for LGTM was onboarded, and he said his team didn't work. And at first, we're really confused because we had lots of users already, and things are working fine. But then we found out that this repo was in an organization that had defined 45 teams. And it also turns out that all these GitHub list API calls, like list teams and list team members, they're paginated. And the page size is 30 by default. And it turned out he happened to pick one of those teams that was in that second set. And so when his team didn't load, he got back an error. And when this happened, we realized we had to add pagination support. No matter how big we set our page size to, someone would come up with something bigger. And in order to paginate the list of teams, we had to turn these 2 lines of code into this. And in order to paginate the members of a team, it turned these 2 lines of code into this. And while this approach fixes the bug, it makes the code quite a bit longer, and it repeats itself quite a bit. And this got me thinking, is there a way to address this? And if you look at this code, it's actually really similar. I'm not going to go through it right now, but really, it's the same thing over and over. List team and list team members, they both paginate in very similar ways, but they expect parameters of different types, and they return back very different data. And if these were the only places in the code we had to paginate, we might have just left it as is. But there are 10 more locations in our code base with the exact same issue. And we didn't want to have to repeat this pagination code over and over again, just really small variations. So as I said, I came from the Java world. And I spent actually most of the last 2 decades programming in Java. So I asked myself, how would I solve this problem in Java? And well, you'd probably abstract your code using a generic method that looks something like this. And if you're not familiar with Java, code's pretty similar to the Go code we just saw. You pass in an initial empty list, the data that we need to make the remote call, and a loader, which makes that remote call. You append all the data returned by the loader's getData method to that list that was passed in. You You check if there's any more data to load. And if not, you stop. And if there's still more data to load, you keep on calling the loader again with that next new page. And when you're done, turn back the list. And we've got two more types to define, loader and loader info. Loader is just an interface, provides a way for a client of our generic function to specify where to get the data. And loader info is a simple wrapper class to hold the data return from the loader as well as the next page. Unlike Go, Java does not allow you to return multiple values from a single method call, so you need something like this to do it. And with this code in place, we can now pull down all of the teams with this. In this code, you just pass in an empty array list of the right type and the name of the team, and a closure that calls GitHub to get the teams from GitHub and populates that loader info with the data that came back from the loader and the page and the ID for the next page. So all that logic for building up the list of all the teams is just totally abstracted away. And you could use build complete list to pull down all the users of a team also. And the code is almost exactly the same. The difference is just the types and the API call that you're making. So you pass in an empty array list of the right type, you call GitHub API to return all the team members for an ID, and you return back a loader info with a field of the right type to hold the users. And the solution shows that the power of generics is more than just type-safe containers. Generics allow you to abstract the same algorithm over multiple data types. But Go doesn't have generics. So how do we elegantly solve this problem with Go? I mean, you could use empty interface as just a way to pass untyped input and output parameters around, but that misses the point. It just creates ugly code that subverts the type system and that helps us write correct code. So no, not going to do that. But let's look at those two GitHub API calls again. There are differences, but there are also some data types in common there. So you look at list teams. It takes in a string and a GitHub list options pointer and returns back a slice of GitHub team pointers, a GitHub response pointer, and an error. List team members takes in an int and a GitHub list options pointer, returns back a slice of GitHub user pointers and a GitHub response pointer and an error. So some of those parameters are the same and some are different. Is there a way to pass along the parameters that are the same while still referring to the parameters that are different? So let's step back for a bit, and I promise this is actually going to go somewhere. So one of the most powerful features in Go are closures. Closure just looks like a function declared inside of another function. And so here, we have a function called outer that takes in an int and returns back a slice of ints. Inside of outer, we declare a variable called out and a closure called myClosure. And inside of myClosure, we're going to create a slice and with two elements, the value that was passed into out and the value that was passed into myClosure, and then we're going to assign that slice to out. After we do this, we're going to call a second function called helper and pass it in myClosure. And inside of helper, we're going to call myClosure with the value 4. And after that runs, we'll return that value out. If you actually called outer from our main function here with the value 5, anyone know what you get back? You get back a slice with two values, 5 and 4. And this is actually pretty interesting stuff. That local variable out, it was modified when myClosure was passed to helper and called from there. Right? There's no reference to out inside of helper, but using a closure still allowed it to be modified. So just like structs in Go, closures have state. And the power of closures comes from these few things. First, this is our ability to refer to and modify variables declared in the same function that they're declared in. Secondly, closures can be passed to other functions or even returned back from the declaring function. And when combined with references to local variables, that gives us that interesting behavior. And that behavior, it also provides a solution to our problem. So let's go through the steps. Using the closure technique, we can generate a slice of the type that we need. We can modify that slice in a closure that's passed to a function that does the actual pagination looping. And our closure just needs one argument. GitHub list options pointer has the current page info, and return back two values, a GitHub response pointer and that ubiquitous error. And the function that we pass to the closure, it looks like this. So this is the function we're going to pass to the closure. It looks like this. And the function we're going to actually run the closure in, it looks like this, called build complete list. It takes in the closure we just defined, returns back a GitHub response pointer and an error. And inside of build complete list, we are going to declare a response variable, an error variable, and a GitHub list options variable. We then set up a for loop, and we call that closure with the list options. We break if there was an error or if we're on the last page. And if not, there are more pages to go. We update that next page field inside of our list options, and we loop again. And then when we're done, we return back the response and the error. So this is pretty good. We managed to abstract away most of that business logic. And the client code for loading up a team now looks like this. We declare a slice of type GitHub team pointers, and we call build complete list with a closure that calls the GitHub API to get teams, copies the values returned into that output slice, and returns back the response and the error. And the clients for the members of a team, take a look at that. We declare a slice of type GitHub user pointer. We call build complete list with a closure that calls the GitHub API to get the team members. We copy those values into our output slice and return back the response and the error. So this is very similar to what we just did to get back all of the teams for a particular organization. The only difference is the types of the data that we're working with and the GitHub API call that's being made. And something else, this is really close to what we had before with that Java generic method. The only difference between this and the Java approach is that we access the output slice directly in our closure, but in the Java example, we pass it into that generic function. And this closure technique worked really well for us in LGTM. We were able to convert all of the places in our code that needed pagination to follow this pattern. And the closure approach can be used in many other places in Go code where you return to generics in other languages. Here's another place where the technique can be handy. Accessing public fields across different structs. So we Go developers, we tend to expose public fields rather than define getter and setter methods, and that's okay most of the time. But without methods, you can't use an interface to refer to identical data in two different structs. So what can you do? You can pass in a closure to a function that wraps access to the struct and return the value of the field that you're accessing. So say we have a name field in a struct person, a name field in a struct employee, and a pet owner struct that embeds a person struct inside of it. And let's say we want to write functions to filter out based on name. Normally, you have to define 3 different functions, right? You have one for person, we have one for employee, we have one for pet owner. And it's like the exact same code, right? Same thing over and over again. But by wrapping the access of the field in a closure and wrapping the building of the output slice in another closure, we can abstract away the algorithm for filtering on name, and it allows us to write one function that can handle any type. So here's our name filter function. It takes in a length of the slice, the name to filter on, and 2 closures. One to get the right field, the other to update the output slice. It loops over each element, checks if the name matches, and if it does, it puts it into the output slice. And here's what the client code looks like for an employee. We have a source slice of employee data, didn't put the whole thing up there, and an output slice for filtered employees. We call name filter, we pass in the length of our employee slice, the name we're filtering on, a closure that returns back the name field for our employee, and a closure that updates our output slice. And if we want to use the name filter to process pet owners, it looks just like when we're processing employees. We just pass in different types. So we have our pet owner slice and our output slice. We call name filter the length of the pet owners and the name, and a closure that returns the name for a pet owner, and a second closure that updates the output slice. And I'll grant you this is a little bit of a silly example, but it had to fit on a slide, right? But I think you get the idea. You can use this closure technique to abstract away the differences between types, and in Go, there's lots of places we can use this technique. So does this mean we don't need generics at all in Go? Not entirely. For one thing, using closures in this way, most certainly not generics. If you had to use a design pattern to label this approach, you might say we're using a strategy pattern. And that's fine. Design patterns are the names we give to things that we build to work around features that are missing in languages. And over time, successful design patterns, they get adopted by languages and become built-in features. And we've been talking about generic functions and using closures to simulate them, but we haven't talked about what's actually going on when we make a function call. So can you imagine a language that didn't have any way to call a function? It sounds kind of crazy, right? That's like a basic built-in feature of any programming language. Except that it's not. If you're doing assembly language programming, you have to build function calls with a function call design pattern. So here's a very simplified description of how that works. Say there's some common code in your application. It takes in a 32-bit int, a byte, and a 64-bit int, and will return back a 64-bit int. So each value is a different size, right? You have 4 bytes for a 32-bit int, a byte for a byte, and 8 bytes for a 64-bit int. So how do you pass your data to a function? Well, the way you call a function is you put those values that you want to pass onto the stack, which is a region of shared memory. And you put the return address on the stack. And the return address is the memory location of the next instruction to run when the function returns. And you then jump to that address in memory where the function is located. and the function pulls the values off of the stack and does some work with those values. And when the function is done processing, you do the reverse. The function puts the calculated value back onto the stack, jumps back to the return address, and the instruction at the return address pulls that return value off the stack, and the main program continues. And doing all this by hand is tedious, error-prone work. It's really a great thing that high-level languages do this for you. But understanding what's going on behind the scenes is really helpful, because you can see that in order to pass a value to a function or read that value back, the function and the function's caller need to agree on how big each value actually is. If the sizes don't match between the caller and the callee, your program's going to crash at best, or you have some sort of stack-smashing security hole at worst. And this is one of those places where there are complications in implementing generics in a language like Go. So different types, they can take up a different number of bytes in Go. And in order to properly handle input parameters and return values, you would need a way to know exactly how many bytes each value is. So one way around this is to make every single value the exact same size. And when you wrap up a value in an empty interface, the problem goes away because all empty interfaces are the exact same number of bytes. Under the covers, an interface is implemented as a pair of pointers, one to the type and one to the actual value. And it's that pair of pointers that you put onto the stack. And by the way, that's how Java implemented generics. All objects in Java are actually just pointers to objects. There's nothing in Java like a struct. And since all objects are just passed around via pointers, and all pointers are the same size, methods don't need to worry about the size of the data being passed in or out of it. It's always going to be the same. So imagine you have a class called foo. And foo is one field in the class that's generic. And when we say that the generic fields of type bar, you get something like this in memory. You get a foo pointer that points to this foo memory region, which has an int, and another pointer off to the bar memory region. And when you go from foo having a field of type bar to a field of type zap, the memory layout for a foo doesn't change at all. It's still a foo pointer off of this foo memory region, off to a pointer, off to a zap. And in fact, the Java virtual machine has no concept of generics. It's all implemented by the compiler. Once the compiler verifies that types make sense, all the generic type information is removed, and casts are put into place. In Go terms, the Java generics automates passing around empty interfaces and casting them to the right type when you need them. And these design decisions in Java, they have some consequences. People make fun of that ugly syntax in Java around generics, but there's some ugly in the implementation compromises too. So you can't use Java generics with primitive types like ints or longs. Different primitive types are different sizes. So you can't have a single field to hold them or a single method that can accept or return them. And since all type information is stripped by the compiler, you can't create new objects of the same type as a generic parameter that's passed into a method. And all those extra pointers, that's one of the reasons why Java programs use so much more memory than Go programs. And the Java community, they're well aware of all these issues, and there's talking about ways to address them, but Java 9 just came out like 2 weeks ago, and the next version of Java is years away when they finally get around to this. And when they do, it's just going to add even more complexity to the language. So as we're looking for a way to add generics to Go, the Java implementation approach is not very appealing. So when we ask for generics in Go, part of what we're asking for is extending that built-in implementation of the function call design pattern. And that way we can access items of different sizes without having them have a shared interface. And for now, we can use techniques like passing enclosures to work around this limitation. It's a stopgap until the Go team finds a clean, coherent way to provide generics in Go. And while using closures in this way does work, you need to be careful because making a mistake can cause problems in your program. So the biggest drawback to using closures as a replacement for generics is that they simply don't work in all cases. So even if the algorithms are identical, you can't use this technique if none of the data types are the same. It's not possible, for example, to walk through all the items in a map of any type. We saw how to build a filter for any type of slice, but if you want to work with a map, you're out of luck. The reason why that happens is all slices have something in common. There's an int for the index value. And that means you have a common type for a parameter that's passed into the closure to refer to each item in the slice. But with maps, there's no type in common. So let's look at a couple of simple sets built on top of maps and look what it takes to implement a simple union function for them. So here's a set for strings and a function that unions two of these string sets together. And here is a set for integers and its union function. This is incredibly similar to the code we just saw, just a few characters different, right? But the closure technique won't help us remove any of that repetition here. The only way to range over a map requires you to have that map itself. And the keys are two different maps or two entirely different types. And because of this, we can't build a generic union set that's going to work for both string sets and int sets. There's no types in common to abstract over. Now, if you really wanted to try, you could do it. You could pass the maps into your function as empty interface parameters, use reflection to build the output map, and walk over the input maps. I'm not going to show that code because it's ugly and it's hard to follow. The goal is to write code that feels like Go, and that's not it. So at that point, it's probably just a better idea to just make copies of your code. Another drawback to using closures as a replacement for generics is that they work via side effects. Modern software development discourages side effects because they make it harder to reason about the flow of your data. It's easier to test and understand a program when the functions only rely on data that's passed in, only modify data that's created within the function. When a function relies on data that's set up somewhere else in the program and modifies that non-local data, there's an invisible dependency that has to be maintained. And when you pass around a closure, you do potentially turn local state into non-local data. The data needs to be managed. It can't be called from multiple Go routines without proper locking. And there's no way to know that a passed-in function is a closure. You have to understand that closure itself flows through your program. However, these drawbacks, they don't make the closure technique bad. They just mean you need to use it when it's appropriate and be careful. Rather than just pine for generics in Go, we can use the tools that it does have to help us work around this limitation. And the art of programming, really, it's just often just the art of compromise. There are a lot of tensions that push us towards different solutions, different directions, depending on the situation. And Go is designed as a language that favors fewer, simpler, orthogonal features over complexity. And while we as a community figure out how to make a generic solution that fits our needs, we can use the closure pattern to reduce boilerplate and get many of the things that we want out of generic programming. So thanks for your time. Have any questions?
Got a bingo card. All right.
Thank you very much, John.
Thank you, John. If you have questions, we encourage you to go to lunch with John, because we don't have any time for him now. But John, that was fantastic. Thank you very much.
Excellent.